Okay, question 28 says, if we find that there's a linear correlation between the concentration of carbon dioxide in our atmosphere and the global temperature, does that indicate that the changes in the concentration of carbon dioxide cause the changes in global temperature? I don't know if the emphasis is on my voice. Kind of already lead to the answer here, but no. The presence of linear correlation between two variables does not imply that one of the variables is the cause of the other. In fact, it could be something completely different. In the case of what this is making reference to, carbon dioxide and global warming, maybe there's some X factor that carbon dioxide is remaining in our atmosphere more because of some sort of cyclic change in the rotation of the Earth, or the tilt of the Earth, or the change in the orbit around the sun, or whatever, which that same X factor is also causing global temperatures to go up, because with this new tilt or this new orbit, we're closer to the sun or spend more time closer. I don't know. Anyway, I'm not trying to get political on you. If you guys thought that was political, you're crazy. It's not. But anyway, their correlation does not imply causation is the phrase you want to remember here. There could be some other X factor. Number 29. The heights in inches and pulse rates in beats per minute for a sample of 8 women measured. So good, that's paired data because they're the same 8 women and they've done the inches and beats per minute. Using technology with the paired data of height / pulse rate data, the linear correlation coefficient is found to be 0.648. Is there sufficient evidence to support the claim that there is linear correlation between the heights of the pulse rates and the pulse rates of women? And we are going to use a 5% level of significance. Okay, so all we need to do is go to the table and compare this to the critical value. If it is above the critical value, this is our R value, remember? Our Pearson R. If it's above, then we will say that there is correlation, and if it's below, we'll say there isn't. So let's get the table open here. Keep in mind what we're essentially doing is we're doing a hypothesis test. We're assuming that there is no correlation, so rho is 0, and then we're testing to see if that's true. So what essentially happens is we compare it to these critical values, and if the R value is, the correlation coefficient is bigger, then we are going to reject the null. So we're going to reject the assumption that there was no correlation. And if you're rejecting that there is no correlation, we're supporting that there is. That's an oversimplification, but that pretty much does it. So we had 8 women, and we are using a significance level of 5%, but our correlation coefficient, our correlation coefficient was only 648 thousandths, and it needs to be more extreme than this, which is 707 thousandths, which means, I'm sorry, because the absolute value of that is less than the critical value, there is not sufficient evidence to warrant rejection. We're not going to be able to reject the null, so there's not sufficient evidence to support the claim that there is correlation. If you need more help on that, go watch the videos or reread the section. This is clearly from section 10.2. Okay, use the given data to do parts A through C. Use significance level of 5%. And this is apparently supposed to be paired data. Doesn't seem to be telling us what the relevance is, if these are pounds or feet or whatever. But I can run the whole thing right here in StatCrunch. First thing you want to do is you want to do a scatter plot. So I'm going to go to graph, scatter plot, and I'll put the x's in for x and the y's in for y. Leave everything else as it is. I'm going to plot the points. This is kind of unnecessary because the tool that we use to do the correlation calculation, or the coefficient calculation, and run the test, it will do this for us. But we see here that there seems to be actually arguably a pretty tight pattern, but it's not linear, right? If you keep following down, it looks actually quadratic is what I was going to say. Like an upside down parabola, shifted and up. So anyway, that was important because you really shouldn't be running these tests if they don't meet the requirements, and we were supposed to visualize a linear pattern. Okay, let's mark that. That was A. Find the linear correlation coefficient R, then determine whether there is sufficient evidence to support the claim that there is a linear correlation between the two variables. All right, let's go on and just play their game because really at this point it's a joke. I'm going to hit stat, and I've got regression right here. Simple linear regression, because we were supposed to be assuming it was going to have a linear regression. X for x, y for y. And you can leave hypothesis test there. So see how it's assuming that there is no correlation, and we run the test against that idea. Level of significance 95, that's fine, because then that's using a significance level of 5%, or alpha is 5. Well, you can actually use this graph. You don't have to. You could uncheck this, but we'll go ahead and have the graph come out with it. It'll be on page 2. Okay, so then here we go. We've got our correlation coefficient right here. Trying to see if I can select that. But I'll just go ahead and choose 3 decimals, 816 thousandths. Okay, and then I'm going to go back to it. Then if we would have gone to the second page, we would have seen that, you know, our best fit line here is not fitting very well because it wasn't really having a linear pattern to begin with. Okay, so determine if there's sufficient evidence to support the claim. Well, I'll go ahead and open this table now. If we have an R value of 816 thousandths and we're using a significance level of 5%, we are going to go ahead in this column for our, I don't want to count those pieces of data, and I don't have to, because I can see right here that there are 11. So there are 11 pairs, which means I'm going to go down to 11 over here, and we are definitely above that, right? Hooray, good, right? No. Actually, it's just a bunch, it's an illusion. So it says that there is sufficient evidence to support the claim that there's a linear correlation. Yeah, using that information, but it's an illusion. Identify the feature of the data that would be missed if part B was completed without constructing the scatter plot. Okay, what would be missed was the scatter plot reveals a distinct pattern that is not a straight line pattern. So the work done is really nonsense. There is a term that I've heard for this that applies to all of our hypothesis tests and all the data that we collect. In fact, if we're collecting data that's not simple randomly sampled, you'll hear this phrase sometimes: crap in, crap out. And that's kind of like what we have here. This is not data that support running a linear correlation this test. Let's see if we have time for one more in this video. Oh yeah, let's try this. Hold on, what time is it? Yeah, we're only at 10 minutes. Okay, so listed below are the budgets in millions of dollars and the gross receipts in millions of dollars for randomly selected movies. Construct a scatter plot, find the linear correlation coefficient R and the p-value using significance level 5%. If there is sufficient evidence to conclude that there is a linear correlation between the budgets and the gross receipts, is there sufficient evidence to conclude that there's correlation? Do the results change if the actual budgets listed are put in, millions instead of like this, where it's in millions, but they're just showing the whole number part. And I think you can answer that right now. But either way, so let's run the test. All right, so we got 7 pieces of data. We're going to run a scatter plot. Whoa, you got this guy way up here. Okay. So, with this one up here, it makes it harder to see, but you can kind of see there's this linear pattern. We're actually supposed to throw those out, right? Sorry, I didn't use the notation yet. So our null will be that we assume that there is no linear correlation. So rho would be 0. That's A, B, and D. And if rho is 0, then you're either going to be negative or you're going to be positive, so less than or equal to. And so we're going to choose this to not equal, because that gives us both tails for the alternative statement. Construct the scatter plot. We saw it look like this. That was choice A. Find the linear correlation coefficient R. I can now go to stat, regression, simple linear. And just keep everything the way it is. I should double check what significance level we're using, but I'm assuming it's 5%. Okay. The value is 901. The test statistic T is, I think they give that to us here when we run it. Let's see here. So remember, this is this test statistic from the student T distribution, where we are going to use a degree of freedom of 1, 2, 3, 4, 5, 6, 7. We'll use 6 then, degrees of freedom. And go, I guess I can do it either on StatCrunch or just use the table. We're using a significance level of 5%. So we want to have, oh, you know what am I doing? I'm sorry. I'm all over the place. I'm not trying to find the critical value. I'm trying to find the test statistic. So anyway, so I'm going to go here. This is page 507. As a reminder. And then it says, you can run it, find the test statistic, or I can use software or the TA83 84 calculator. It is already, I believe it's already calculated when I use StatCrunch. Yeah, so it's under slope here, test statistic, 4.6, and I'm not sure how many decimals we're going to go. 3 decimals. Well, that makes sense because usually that's what we do for t-value test statistics, t-scores. So 4.649. And actually, just pause for a second. I'm going to go ahead and run this on the TI-83 calculator. And I am getting the same number. So if you want to see quickly how to run it here, you go under, if I can get this to work, you go under Stat, Edit, for list 1, put your X's, for list 2, put your Y's, and then go back to the home screen, Stat, go to Tests, and it on mine is E, Lin Reg T Test. So it's going to do the hypothesis test technique. Do the linear regression. List 1 X, list 2 Y, frequency 1. This is paired data, but 1 sample. Your hypothesis test, and remember we're using the idea that rho is 0, but there's no correlation, and we're testing against that. And then just go ahead and run it, calculate. And it gives you your test statistic right there. And it also gives you your p-value, in fact. Actually, let me check. So our p-value is 0.0056. But is that also on the, yeah, on the StatCrunch? Here's a parameter slope and test statistic 4.68, and here's the p-value 0.0056. So it also did it there, which is going to be your better tool when you're taking the test, since you're already going to have the web page up and you're going to have the StatCrunch tool right there. Okay, because the p-value is, in this case, less than the significance level. Remember, if it is less than the significance level, that means that all of the p-value is falling into the critical region. So we're going to, sorry, let me first state the initial criterion, the decision criterion. If it's less than alpha or equal to alpha even, we will reject the null. So we're rejecting that there is no correlation, which means that we're essentially saying that there is correlation. So there is sufficient evidence to support the claim that there is a linear correlation between these. Do the results change if we use these? Well, what do you think? I can actually go through the numbers, but would they change or not change? So I would say there would be no result in the change, no change in the results. Oh, there's that last question. Did I make a mistake on that thinking or misread it? So anyway, the rest I'm not going to look at. Let's see. So we symbolically stated it. We graphed the plot there. Oh, they wanted 3 decimals here. Oh, we could give ourselves a headache after the final's over and double check in the midterm. But if these things come up where you rounded it wrong here, I will make a consideration, but please don't. You're probably not going to be as rusty as I am with paying attention to those details because you've been doing the homework regularly. But so anyway, we see here that there would be no change in the result. It would be the same linear correlation coefficient. So nothing else would change. And I ran it again just to show you that we've got the same correlation coefficient, same test statistic then obviously, same p-value then obviously. I will state that I think some people may misread what they're asking you to think about, because they said, do the results change if the actual budgets are listed instead of saying just 61 representing 61 million, but actually writing 61 million? And then some people take that to mean only changing the budgets right here, the X values, and then they don't change the gross. And if you do that, then yes, there will be a change, and it won't fall in line with these. It'll be something totally different. But what they were meaning by this question that they asked and then restated is, what about if you change the budget and the receipts? Okay, anyway, watch out for the rounding errors. Here's question. Well, there were those 3 or 4 questions there.